Welcome. In this lecture we will discuss the origin of rock salt formations. This pictures a three-dimensional seismic interpretation of such formation in the northeast of the Netherlands. And on next picture I will show you where exactly. Well, these mountains of massive salt rise up to 3.5 kilometers high, and right in the middle is where I live. But do I live in a mountainous area? No, it is a very flat region. And these formations are hidden underneath, buried under several kilometers of sand, clay and chalk deposited out of water. Even the tops are buried under the surface. Rock salt formations contain hundreds of thousands cubic kilometers of salt, and I will show you some. This is such a piece of rock salt. It's a massive stone. No porosities at all. It's pure salt. These large formations are found on every continent around the world. These salt formations are commonly referred to as evaporites because they are considered to have been formed by the evaporation of seawater. The evaporite model requires the evaporation of hundreds of kilometers of depth of seawater, a process that would require vast periods of time, far longer than biblical timescale. Consequently, evaporites have been used as an argument against young Earth geology. However, there are major problems with the evaporite model, and we will look into that in four steps. Firstly, we will consider the origin of salt from a helicopter point of view. And secondly, we will consider the origin of the detailed layering within the salt. Thirdly, we will consider the origin of those huge pillars of salt. And at last, we will consider the origin of the gypsum cap rock, as every pillar is topped off with a gypsum head. And so, let's start from a helicopter point of view. The three-dimensional picture I showed you before is only a small part out. This is a small part in the northeast of the Netherlands. It's only a small part out of the total Zegstein formation, which is a 500,000 square kilometers wide salt formation. And when you push back all the pillars, the thickness may become 1 kilometer in average. To form this Zegstein formation, a 60-fold of seawater needs to be evaporated. So we are talking about 500,000 cubic kilometers of rock salt, and to form that you need a 60-fold of seawater, which is a lot of. But inside the formation we found no fossils, no shells, no algae, no seaweed. The salt is pure, without sand or clay mixed in with it. Well, that makes clear that no evaporation process can count for the origin. And that has been realized. Therefore, many geologists challenge the evaporate model and investigate an origin out of hot water vents in volcanoes areas. For example, this model. Here you see a magma chamber underneath a porous rock, underneath seawater. The high temperature inside the magma chamber will cause a slow water current through the rock. And when the water exceeds supercritical temperatures, the salt will separate, forming a salt stock within the rock. In case of the Zegstein, it requires a magma chamber of enormous dimensions. as the magma chamber has to underlie a surface of 500,000 square kilometers wide and stay there for millions of years, as the system is very slow. The amount of water that has to pass through is a 60-fold of the 500,000 cube of salt. So the system fails. And it fails anyway, as the resulting salt stock will not be pure. So hydrothermal models won't fit the problem. Let's zoom out and look worldwide. Salt formations are found worldwide upon every continent. This map is far from complete. There are many more. What can we conclude from this helicopter view? Well, firstly, we see a strong association with the first fossil fuel reserves, for example, in the Persian Gulf and in the Gulf of Mexico. And secondly, we see several salt formations in the Great Rift in Africa, which is a 6,000 kilometer long tear in the crust. There we find the Danakil Desert, which is a small salt formation, but it fits in the tear up to 5 kilometers deep. And farther north we find a formation upon the bottom of the Red Sea. A large formation which fills the tear underneath up to several kilometers deep. And farther north we find the Dead Sea Formation. This salt formation fills the tear to at least 10 kilometers deep, and probably deeper. These findings make very clear that the salt probably came out of tears in the crust. And if so, then salt is from a primary igneous origin. Indeed, salt is having a melting point. And molten salt will behave like a thin fluid. It will run like water, but it is twice as heavy compared to water. So let's consider a huge catastrophe like Noah's flood, where water is delivering lots of sediments, and where loads of organic material was buried. Let's imagine that during that flood, the salt started to flow, covering the floor of a basin with hot liquid salt. That will explain the association of salt with fossil fuel reserves, as the heat of the salt will transform the buried organics into oil, gas and coal and store them underneath the salt. Well, this is what can be concluded from a helicopter point of view. Let's have a look into the very detail now. In salt formations, we find many salts like potassium, magnesium salts and carbonatite, which is igneous rock, by the way. The inside layering of salt formations is very complex, more than can be discussed in this presentation. The two salts that are found most inside are sodium chloride and calcium sulfate. Therefore, I will limit this lecture to those. When we look to the core samples of the zechstein, we find in the upper part hundreds of meters pure salt. This core sample is from the upper few hundreds of meters. When we look to the core samples of the zechstein, we find in the upper part hundreds of meters of solid sodium chloride without interruptions. But the deeper we look, the more calcium sulfate layers have been formed. And this sequence has been repeated twice, which might be explained by two large eruptions. And here you can see how the calcium sulfate layer looks like. The deepest part at the left is pure calcium sulfate, and higher in this layer you can find pure sodium chloride crystals. And note that the primary igneous origin of calcium sulfate is just recognized by geologists since the eruption of the El Chichon in Mexico in 1982. So it's not that far out of the box to deem salt formations as being from a primary igneous origin. Let's check these facts against a thermodynamic model. How will a mixture of two hot liquid salts behave when they cool down below their melting points? And for that question, I consulted a professor from the University of Utrecht. He prepared for me this eutectic phase diagram. The vertical axis represents the temperature and the horizontal axis represents the ratio of the salt. Here it's 100% calcium sulfate and at the other side it's 100% sodium chloride. And the Zechstein formation contains mainly sodium chloride with a relatively small amount of calcium sulfate. And therefore, we have to deal with the left side of the diagram only. In the diagram, the blue vertical line shows the ratio of the melt. The two salts are very well miscible in the liquid state, very well mixable. And following the blue line down, the temperature drops until solidification starts at the so-called left liquidus at this point. At this point, sodium chloride only sodium chloride starts to solidify. Pure sodium chloride is less dense than the liquid, as the liquid contains all the calcium sulfate, which is far more dense. So the solid layer of sodium chloride will float above the liquid salt. Because of the separation of sodium chloride, the melt becomes enriched with calcium sulfate. Therefore, the blue line follows the left liquidus until the eutectic point has been reached. At this point, both salts will solidify. But note that these salts do not form mixed crystals. That means that pure calcium sulfate and pure sodium chloride crystals will be formed. And that is just what we saw in the core samples of the formation. Pure sodium chloride in the upper part and pure calcium sulfate in the lower part. So the details of the formation confirm a primary igneous origin as well. Now we have seen that the salt formations can be explained by a primary igneous origin. They have been erupted out of tears in the earth crust. But as the melt will run like water, the melt will fill up a basin and be left as a horizontal layer of rock salt on the bottom. So how is it possible to find pillars like those hidden in the deep underground all over the world? Mainstream geologists believe that those pillars formed slowly in 80 million of years. And they believe that the layers above the rock salt are more dense than the layers above the rock salt are more dense than the rock salt itself. Therefore, the rock salt has been pushed upwards, slowly and steady. But that's not true. Sand and clay do have a low specific density. Wet sand has a density of 1600 kilos per cube. The chalk layers can be more heavy, but their porosity reduces the specific density strongly. Therefore, the salt with a weight of 2300 kilos is more dense and will stay underneath where it was. A top of a salt pillar can be as big as several tens of square kilometers. That means that complete regions should have been lifted up during the formation of the pillar. And anyone can see that the resulting mountain will be pushed down by its own weight. So the system fails in itself. But what if there has been an interaction between this salt tectonics and plate tectonics? Could that explain those pillars? That could have been the case. That could have been the case if the northern part of the Netherlands were a mountainous area, where mountains were formed like this. But it is not. The Netherlands are flat. Therefore, it cannot have had anything to do with plate tectonics at all. It seems that we have to think out of the box again. And here you see. Here we can see the salt pillars of the Zechstein Formation colored in red. The question is, how did they rise up? Let's again consider that during the flood the salt was erupted, covering the floor of a basin with hot liquid salt. With all the water of the flood above it, the salt will slowly solidify, and this solid crust will float on top of the melt. And then, for any reason, the crust starts to crack. Maybe by volcanic eruptions that cause strong waves in the melt, or by thermal shrink, or whatever. Just imagine that the crust cracked. At this stage, we need to realize that 1 cubic kilometer of molten salt contains enough heat energy to evaporate at least 2/3 of a cubic kilometer of water, which is a lot of energy. The crust on top of the melt did slow down this heat transfer. But inside the cracks where is direct contact between water and hot melt, the heat transfer will restore. I will show you a video. The increasing heat transfer will cause steam generated above the cracks. I've simulated that in the water tank, and here you can see the solid crust floating on the salt. The crack is in the middle, and above the crack steam will be generated, what will lower the density of the water above the crack. And because of the law of communicating vessels, the melt will now be pushed up through the crack. And by doing so, there will be formed more steam above the crack, which will even more lower the density of the water above it, which will force more molten salt up through the crack. And that will continue until balance is reached, conform the law of communicating vessels. If we consider the pillars did rise up to 3.5 kilometers high, and that the melt was twice as dense as water, then the level of water that was involved at that moment in time, was 7 kilometers. So the salt pillars are the silent witnesses of the flood. But now I have to complicate this picture. In the first place, the steam does have its own density. That will surely influence the balance. We can imagine that the steam column probably have been a mixture of water and steam. The density must have been somewhere between 0 and 1000 kilos per cube. Well, let's just value it at 500 kilos per cube. And to complicate the balance even more, we need to think about the origin of the detached pillars that have been found. Here you see one of these. Those type of pillars are detached from the main underground salt body. How did that happen? Obviously, they have been formed in a steam column as well, but the supply of salt out of the main salt body failed. So several cubic kilometers of salt rose up, creating a steam column. But when after a while the heat content was consumed and the steam column decreased, the salt volume had to fall back slowly towards the main salt body. But the main salt body was already covered by sediments. And this shows how fast the water of the flood delivered sediments. Well, this mud does impact the balance slightly. Here you see the water level of the flood that has been required to form salt pillars. This calculation is the result of the law of communicating vessels. The salt pillars are the silent witnesses of a worldwide water flood with a level of 10 kilometers above the main underground salt body. Such a water level seems impossible, but sea level today is still 4 kilometers above the main underground salt body. The 6 kilometer water that is missing today represents only 0.3% of the volume of our planet, which can easily have absorbed it. No problem at all. This is one of the salt pillars in the north of the Netherlands. Can you see how flat our country is? Although the pillars nearly touch the surface, nevertheless, mainstream geologists think that the layers on top of the salt have been pushed up by the formation of the pillar. If that was true, the purple layer underneath, the purple layer on top of the main underground salt layer, would have been found on top of the pillar as well. But it isn't. So, how have those layers been formed in an upward direction in these areas? How have these layers been formed in an upward direction at the sides of the pillar? Well, that is very clear now. Indeed, there were fast circulating water currents because of the steam column above it. And therefore, the layers must have been deposited in this upward direction by fast circulating water. The deposits were deposited by water. In America, they have an amazing formation underneath the Gulf of Mexico, a huge one. The origin of this very complex formation can be explained by a catastrophic genesis only. This is the result of a series of salt eruptions from underneath out of the tears in the crust, in combination with fast depositing of sediments by the water of the flood. And this is the only way to form such a salt formation. I promise you to explain the origin of the gypsum caps that can be found on each salt pillar around the world. They consist out of calcium sulfate. On top of the salt pillars evaporated a huge amount of water, which explains the deposition of minerals, including gypsum. But seawater contains calcium carbonate and sodium chloride as well. So what happened to those salts? Well, calcium carbonate was separated already underneath when the water was heated by the main salt body. This heated water with the remaining salts followed its way up to the top of the pillar where it evaporated. And so all the remaining calcium sulfate and sodium chloride should have been deposited on top of the pillar, which isn't the case. There is only calcium sulfate found. Therefore, from there we can conclude that there was no sodium chloride in the water. That means that Noah's flood was a fresh water flood. Surprise! We discussed briefly the evaporate model and a hydrothermal model and showed that there are major problems with it. I've shown many indications that points us in the direction of a magmatic origin of the salt formations. So I would conclude salt formations are from a primary igneous origin. Salt pillars are the silent witnesses of Noah's flood, which was a freshwater flood, and that made the restart after the flood much easier. Thank you very much for listening. I hope it was encouraging. God bless.